All right, our final topic for Chapter 2 is objects falling under the influence of gravity. Right. So an object moving under the influence of gravity is said to be in a condition of free fall. Right. And prior to about 1600, it was actually assumed that heavier objects naturally fell faster than lighter objects. Right. And you can kind of understand why people thought this. If you drop a bowling ball and a feather, the bowling ball obviously hits the ground faster than the feather. But people had never really done careful experiments to verify this. And so what Galileo did, Galileo Galilei, a famous scientist, philosopher, performed a very careful experiment, and he came to a different conclusion. In his translated words, having observed this experiment, I came to the conclusion that in a medium totally devoid of resistance, all bodies would fall at the same acceleration. So this is the famous Leaning Tower of Pisa experiment that Galileo supposedly performed. And while it's somewhat debatable whether he actually did it at the Leaning Tower of Pisa, the result holds and is generally ascribed to his experiments. So what does he mean by this when he says, devoid of resistance, all bodies will fall at the same acceleration? Well, it turns out that the reason that feathers and bowling balls fall at different rates isn't because of a difference in gravitational pull, but because of a difference in resistance due to air. Right? So if we remove all the air from the room, then in theory, bowling balls and feathers would fall at the same rate, the same acceleration. And so I found this video of from a BBC documentary that I'd like to share with you that does exactly.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. ER, go for drop.
5, 4, cameras on, 2, 1, release.
Okay, so let's work an example along these lines. Let's say that a ball is dropped from rest at a height of 10 meters here on Earth, right? We're gonna assume we're always on the surface of the Earth, and let's assume we're in a giant vacuum chamber, right? Obviously, we're not if we're doing something like the Revell watermelon drop, but we're going to take that approximation that there's no air resistance. What will the velocity of the ball be when it reaches the ground? All right, so let's think about our strategy here. This is clearly a 1D kinematic equation, right? The motion is straight down, and so it's one-dimensional. And what we're going to do, since we've just derived a bunch of equations that have x as the position, just to make the math clear, let's choose the x-axis to point vertically. Right? Normally we use y, and you can simply replace all the x's with y's in your kinematic equations, but let's just call the x-axis vertical for today. And we're going to choose the positive x-axis to point upward. That's our normal convention. The positive points up. Our goal then is to calculate a velocity. right? That's the question. What's the velocity of the ball when it reaches the ground? We're given a displacement. We know that it travels 10 meters from start to finish, and we know its starting velocity, right? We're told that it starts from rest, which means its velocity initially is 0. The acceleration is due to gravity, right? Gravity is the thing that pulls things down and speeds them up as they fall. And gravity points downward, which is in the negative x direction, right? We know that things get accelerated downward when you let them go. And with our definition of choosing the x-axis to point up, then we have gravity pointing in the negative x direction. That's important to keep track of. Notice that they don't tell us anything about time, right? They don't say how long it's in free fall for. They don't say what time we started or what time it finished. So no information about time is either given, and we're not asked for it. We're not asked to solve for how much time. Okay. So since there's no time information either required or given, then it's a good guess that a good starting point would be our kinematic equation that has nothing to do with time, right? And if we look at our list of 4 kinematic equations, then the one that has nothing to do with time is this one, right? Final velocity squared is the initial velocity squared plus twice of the acceleration times the displacement. Excuse me. So we start from rest, which means vi is equal to 0, and the acceleration due to gravity is directed downward, which is negative x. So we will write the acceleration is negative g, right? And g is traditionally written as a positive number. That's plus 9.8. We'll have that on the next slide. But we know that gravity is pulling us downward, and the downward direction is negative x, right? So the acceleration has to be negative. So we write a is equal to minus g. Substituting in, we have vf squared is equal to the initial velocity is 0, so we drop that term. The acceleration is in the negative x direction with a magnitude of g, 9.8, so we plug that in, minus 2g times the delta x. And that gives us a solution that says the final velocity is just the square root of 2g delta x. All right, so let's hold on to that solution. All right, now we can go ahead and plug in some numbers and get a numerical value for our answer. We have velocity is equal to the square root of minus 2g delta x. We note that g, which is the acceleration due to gravity when standing on the surface of the Earth, is listed by convention as positive 9.8 meters per second squared. But the acceleration due to gravity is down, so the positive axis is up, which again tells us that g enters the equation with a minus sign. Also, the ball falls down and the positive axis is up, right? So that means the final position is going to be more negative than the initial position, right? So if it goes from up here to down here, then the change in position is negative. All right, so let's go look at what we got. Final velocity is square root of 2g delta x with a minus sign. So minus 2, plug in the positive value for g by convention, 9.8 meters per second squared. Plug in that delta x is actually negative because it's going down. And we end up with the square root of a positive number, which is good. Turns out to be exactly the square root of 196 is exactly 14 squared. So the square root of that gives us 14 meters per second. And that's our final answer. All right.